right, so our goal with the change of variables with Jacobians is to take what might be a clunky region to integrate over and turn it into a region that makes our integration simpler. And we've seen that when we converted to polar coordinates or triple integrals to spherical coordinates and cylindrical coordinates. The goal is always to make your integral easier. So here I've got another example. I'm looking at a region bounded by the lines here on your screen. And I've already sketched these for you. I'm confident that you can sketch equations of lines. So we're looking at this, this blue shaded region. It's going to be helpful to know these points. Whoops, I've still got the highlighter. These points of intersection on these regions. So let me just tell you what those are. Again, I'm confident you could find these if you had to, right? You're just going to set the equations of the two lines equal and solve for x and y. All right, so this point here is 4/3, 8/3. This point on the right is 8/3, 4/3. This point here is 2/3, 1/3. And finally, the point here is -2/3, 5/3. All right, now you can imagine if you had an integral that you were integrating over this region R, you would have to do quite a bit of work to either use a vertically simple or horizontally simple region. Your limits of integration are going to change based on where in this figure you are. Okay, so we want to use Jacobians to translate this into, say, a rectangular figure that's upright that makes it a little bit easier to handle. So what I'm going to do is let u be x plus y and v be x minus 2y. Now let's think about what happens to the boundaries in the xy plane and in the uv plane. So I'm going to make a little table here. Boundaries in the xy plane and boundaries in the uv plane. Okay, in the xy plane, these pink and blue lines are my boundaries, right? So I have x plus y equals 1, x plus y equals 4, x minus 2y equals 0, and x minus 2y equals -4. Now you can see using this translation, u is x plus y and v is x minus 2y. I've already got this set up as u equals 1. So my boundary in the uv plane is just u equals 1, u equals 4. This is x minus 2y is v, so that's going to be v equals 0. And v equals -4. Now here I wrote u and v as functions of x and y, but really I want my translation to go from the uv plane to the xy plane. So all I need to do is take these equations and solve for x and y in terms of u and v. Now again, this is something that I'm confident you could handle on your own. So for the sake of time, I'm not going to do it here in the video. You should try it on your own, and if you get stuck, please shoot me an email and I can help you. All right, but if I rearrange, what I get is x equals 1/3 2u plus v, and y equals 1/3 u minus v. So this is the definition of my translation from, say, S to R, where T of UV is 1/3 2u plus v, comma 1/3 u minus v. Okay, let's make an observation. What happens, well, let's do it this way. Let's sketch the region S. So now I'm on the UV plane, and I have my boundaries listed here. So U goes from 1 to 4, and V goes from 0 to -4. Here's -4. 1, 2. So here is the region S, and here are the corners of that region. What are these corners? Let me highlight S. Well, I've got the point 4, 0, 1, 0, 4, -4, and 1, -4. What I want you to notice is that these points, these corners here, map to the the 4 corners up here in my region R. So let's see that. Let's look at T of, say, 1, 0. That's going to be 1/3 2 times 1 plus 0, 1/3 1 minus 0. That gives me the point 2/3 1/3. That's this corner point here. So this point gets mapped down here. And so on. So T of 4, 0 is going to give me 1/3 2 times 4 plus 0, 1/3 2 minus 0. That's the point 8/3 2/3. T of 1, -4 is the point 1/3 times 2 times 1 minus 4, 1/3 times 1 minus -4. This is my -2/3, 4/3. And finally, T of 4, -4 is going to give me 4/3, 8/3. All right, so the corners map to the corners of your original region. All right, let's do one more example here. Let's describe the region S. Example. If R is the region given by the ellipse x squared plus y squared over 36 equals 1, and x equals u over 2 and y equals 3v, defines my transformation T. Okay, so what I have is T of uv is u over 2, 3v is my xy. And so I can plug that into my equation for my region R here. So that tells me that u over 2 squared plus 3v squared over 36 equals 1. So what does that give me? U squared over 4 plus I'm going to have a 9v squared over 36, which reduces to v squared over 4 equals 1. And I can multiply both sides by 4 to get u squared plus v squared equals 4. What is this? This is a circle of radius 2. Okay, so my region S is just a circle of radius 2, and you can see how that, in some sense, is simpler than dealing with this ellipse that you started with.